We're on the last section of chapter 10, so chapter 10, section 5, and we're going to talk about in this section how the citrate cycle interacts with a bunch of different cycles within the body. So the citrate cycle we know generates, right, our bulk of redox power for energy conversion. It oxidizes acetyl-CoA to NADH and FADH2, but it also provides precursors, biosynthetic precursors for other pathways. So we call the citrate cycle an amphibolic pathway. An amphibolic pathway, remember amphipathic, right? Something that is positive polar on one side and non-polar on the other side, right? Two different things. And we call it amphibolic because it can be catabolic or it can be anabolic. So if you think about the anabolic part of it, well, actually, no, we know already about the catabolic, right? So catabolic is our oxidation of our acetyl-CoA, right? But anabolic, this is where we are making precursors for other pathways like fatty acids, like amino acids, like heme synthesis. So all of those things are interrelated. We're making precursors for these molecules. So what I want to do is kind of zoom in on here so that you can kind of see the different biomolecules that serve as precursors. So if we look first at citrate, So if we look first at citrate and malate, so malate can be converted from oxaloacetate into malate. So we can have malate kind of build up. And what we can do is we can convert these things to fatty acids. So you can make those fatty acids when you don't need to go through the citrate cycle. You know, your cell's not always going to be going through the citrate cycle. Maybe you don't need to produce those energy carrying molecules. You don't need to go on to the electron transport chain. What else can you do? Well, you also need to manufacture things that are important to your body, like fatty acids or like cholesterol, right? So malate and citrate can do that. You also have, here we go, oxaloacetate here, and alpha ketoglutarate that can participate in amino acid synthesis. Right? And then last but not least, you have succinyl-CoA that can participate in heme biosynthesis. And so it's really important to understand that there are links between these different biosynthetic pathways and that we can interconvert between the two, right? Okay, so we also have Anaplerotic reactions. So these are reactions that are going to basically replenish our citrate cycle intermediates that have been basically shuttled off to other metabolic pathways, right? When you shuttle them off and then your body goes, oh, I really need to go through the citrate cycle so that I can get some energy. So pyruvate carboxylase is one of them. Pyruvate carboxylase will actually convert pyruvate directly to oxaloacetate, right? And why do they call it, well, so the Latin, I know this is probably a term you don't know, anaplerotic. Ana is up, and then the pleroticosis, I think that's the Latin derivative, is to fill. So pyruvate decarboxylase reaction will fill up the citrate cycle by providing oxaloacetate. Right, and this is a reaction that requires biotin. So biotin is another one of those vitamins, but you don't really need to take it as a supplement because it's in so many of the different foods that we eat, and you only need a teeny tiny bit of it. That is not really important. So you can also have phosphoenolpyruvate carboxylase. This one is only present in plants, in yeast, and bacteria. So this is one we can't do. This is one that replenishes oxaloacetate, right? We've basically lost the ability to do this because yeast and bacteria can do it. And so we don't really need to. And so we have evolutionarily lost the ability to do this. But we can replenish oxaloacetate with this enzyme, right? And so here's our phosphoenolpyruvate carboxylate. We can start with phosphoenolpyruvate, which can come from pyruvate, and we can convert that all the way over to oxaloacetate. And so this is just another way that we can get around our needed requirements for the citrate cycle. I don't want you to think about it as a linear pathway where we have to go through this step to get to that step, right? There are lots of interconnected pathways and ways for us to fulfill the need for either using the citrate cycle or kind of shunting things off to different places. So it's very adaptable and interconnected. And so you don't, not that you necessarily have to know every single interconnection point, but you have to understand that you can use these substrates for different biosynthetic pathways. And when those biosynthetic pathways need to be shut off and you need to come back to the citrate cycle, we can do that. All right, y'all have a good rest of your day. That is the end of chapter 10.